Hello everyone, this is Felix from GM Wolf. Today we're going to be looking at how we can make a very simple pool game, like the one you're seeing on screen right now, where you can hit the cue ball like so, and the other pool balls will react. To make this game, we'll be using Box2D, which is the built-in physics engine into Gamemaker Studio, which makes it very easy to use when you try to implement physics into your game. So let's first have a look at the project file I provided in the description below, which we're going to start working on. So we have a couple of sprites and a background. So the first sprite is the ball sprite, which has two images, the first one being the plain ball and the second being the striped ball. And it is a 16 by 16 image which is centered. We also have a cue, which is 128 pixels long and 6 pixels high. This has its origin set to 128 to the right and centered, which allows it to have the which allows its origin to be at the tip of your cue, and which makes making it revolve around your ball a lot easier. We also have a hole sprite. This is used simply as a collision sprite to represent where the holes are found. And we have our side sprite, which represents each of the little bouncy pads you find along the sides of your pool table. So we also have a background, of course, which is just a large green background we're going to be using to represent the floor, the surface of our pool table. So first of all, we need to create our ball object, and we're going to start off with our cue ball. So we can do obj underscore ball underscore cue as our new object. We're going to select our ball sprite, and we're going to make sure we tick use physics. This will allow Gamemaker Studio to know that this is a physics object. Then all of your default behavior, such as speed, h-speed, v-speed, and direction, will no longer apply. It will instead be using the physics engine built into Gamemaker Studio. Under collision shape, you can decide what shape your collision object has, and we're going to be using circles because balls are circles. And then we want to click modify collision shape to make sure that our circle is properly centered above our sprite. If it is set over here, like so, it is because you have not centered your ball sprite. So make sure you position the circle shape perfectly over your object. Next, we want to modify our variables, our density, restitution, etc. variables for our physics object. So the first is density, which represents how heavy your ball is going to be. And we're going to leave it at 0.5 as it seems to be an okay value. The restitution represents how much your objects will bounce off each other. And in a pool game, you want a really high restitution. You want your balls to have really nice bouncy collisions. And so we're going to set it at 0.8. Collision group, we're going to leave at 0 as we're not going to be messing around with those. Linear dampening represents how much your object will slow down. Now in a perfect vacuum you would set that to 0 as there's nothing to stop your ball. However, our ball is actually rolling on a felt surface, and this has a pretty high friction because felt is deforming under your ball. Therefore you want a pretty high linear dampening too, which allows your ball to stop. So we're going to be using 0.8 for this value. Same goes with angular dampening for similar reasons. I'm going to leave friction at 0.2 as it seems to be an okay value for pool balls. Next, we're going to press OK and duplicate our object and have this be called obj underscore ball underscore color, and this will represent all the other balls on your pool table. We are going to leave the same values over here and make sure our collision shape is still okay, which it is. So we can now press OK, and we can start dealing with our physics object. So we want our cue ball to collide with our color balls. However, to do so, we would need to add a collision event inside our cue ball with our color object. And later on, when we want it to collide with the sides, we'll also have to add a collision event for that and for the color balls and the sides again. So there's quite a bit of work to do. So instead, what we're going to do is create a new object called par_physics, which will represent all the physics objects. And this will only have one event, which will be the collision event with itself. And all we're going to add is a comment, and you can put whatever you like in here. I'm just going to write collide so that we have a collision event with itself. This will allow Gamemaker Studio to know that any object which is a child of par physics has to collide with any object which is also a child of par physics. So we can now create a new object called par ball so that we can represent all the balls. Make sure that is a child of par physics. Press OK. And then make sure obj ball Q is a child of par ball, and make sure obj ball color is also a child of par ball. So now we can set up our physics room by creating a new room, calling it rm_main, and then under the physics tab, check room is physics world. This will tell Gamemaker Studio that this room contains physics objects, and you should be using physics to calculate these physics objects. So we have some physical world properties over here. The first is gravity. And well, we don't want any gravity because our game is viewed from top down. And so there isn't really a gravity component to any of this. So we're just going to set gravity Y and gravity X to 0. Next we have pixels to meters. We're going to leave this as is, but if you wanted to get your game to be as physically accurate as you could, you would want to set this pixels to meters so that your balls are about the same real life size of a cue ball and a pool ball to make sure that you get accurate physics simulations. But for the purposes of this video, we're just going to leave it at 0.1. Now we can place our objects. So we're going to place one cue ball over here, and we're going to add, change the snapping to 8 and 8, and add a couple color balls over here next to it so we can test our system. Like so, something quite simple. Press OK, and now we can press play and see if our physics objects are properly set inside our world. So as you can see, the objects are there, they're not falling, which they would be if you forgot to change our gravity, and they all seem to be behaving alright, apart from the fact they're blinking really quickly. That is because we have an animation with our sprite. So what we want to do is under our par ball object, add an event, create event, and add a piece of code. And here we're just going to disable the animation by writing image_speed is equal to 0. This will set the image speed to 0 and effectively disabling the animation for this object. And any child object for that matter, which includes the cue ball and the color ball. Now, our cue ball right now doesn't do anything, it doesn't react. So what we're going to do is first of all add the ability to see our cue around the ball when it's so in order to aim. So let's open up our cue ball and add an event, and we're going to add the create event. We're going to add a couple pieces of code. The first is going to be mouse_click_X, and we're going to set it to 0, and this will represent the X position of where you last clicked, where you last pressed the button down. And this will be useful in order to lock our direction when we're trying to hit our ball, and also find with what strength we want to hit our ball. And we're going to do the same with mouse_click_Y to get the Y position. We're also going to have a Boolean variable called pulling, and we're going to set it to false, and this represents whether or not you're pulling back on your cue before hitting your ball. So we're going to just call that pulling. Press OK, and now we can go inside the draw event of our object, and we're going to add first of all a small piece of code which will draw our cue around our ball when we are before we hit it, before we pull it back even. So we're going to add first of all, we're going to have to find the directional vector between our mouse and our object. So find directional vector. We are going to create new variable, a temporary variable that is, so that because we only need it for this small piece of code, called dir_vec_x, so the x component of our directional vector, and we're going to set it to x minus mouse_x. We're going to do the same for y, so var dir_vec_y is equal to y minus mouse_y. So now we have a directional vector. However, its length is also the distance between your mouse and your object. And for the rest of this code, we're going to need it to have a length of 1. So we're going to need to be able to find the length of our vector. And because we're going to do this a lot, well, at least a couple times in this project, we're actually going to write a script that will help us do that. So we're going to create a new script and call it vector_length. And we're just going to tell Gamemaker Studio what this takes. So you can put 3 forward slashes, write vector_length, exactly as you wrote it in the script name. And we're going to just say what variables it can take. So it will take a vector x and a vector y. Now this script will return the length of this vector. So to do so, we're going to write the keyword return and then square root of the square of argument 0 plus the square of argument 1. So essentially we're using Pythagoras to calculate the length of our vector, using argument 0 as the x component and argument 1 as the y component. We can press OK, and here we have var length is equal to vector_length direction vector x, dir_vec_y. So now we have the length of our vector. We can normalize our directional vector. To do so, we just have to divide each component by the length. And this can be done by writing dir_vec_x divided is equal to length, and direction vector y divided is equal to length as well. So now we have normalized our directional vector. What this means is it now has a length of 1. Now we can calculate where the q is. So get q position, and we're gonna say that q_x is equal to the x position of the ball minus our directional vector dir_vec_x times an offset of 16 pixels, and q_y is equal to y minus our directional vector times 16. Now we're going to be using qx, and we're going to instantiate it 2 different ways. So right now we're instantiating it just by having our mouse around it, but later on we're also going to need to change it depending on how far away your mouse is from the original place you clicked. So essentially what I mean to say is that we need to first of all declare our variables up here. So q_x, q_y, and q_direction, qdir. And don't forget to put a semicolon to say that you're done declaring variables. So now we can actually get the q direction by doing q_dir is equal to point direction. We want the x position of the q, the y position of the q, and the x and y position of your ball. We can now draw our q by writing draw_sprite_x spr_q. The subimage is going to be 0. The x position is q underscore x. The y position is q underscore y. The x scale and y scale are both 1. And the rotation is q underscore dir. The color is simply c underscore white. And the alpha is also 1. So just to make sure all the code can be seen on screen, here you go. Now, if we leave this inside the draw event, the ball will no longer draw itself, but we still want it to draw itself, so we're just going to go at the very top of this whole piece of code and write draw underscore self to make sure that our ball still draws itself. So now if we press play, what we should be able to see is a cue that can orbit around your ball. So as you can see, we have our cue ball and we have our cue orbiting around it, but we cannot yet pull it back or fire or hit our ball. So all we have is our cue orbiting. Now, as you can see, we have another problem, and that is that our ball is still flashing with the striped animation. However, you see that the other ones are not. This is because of how Gamemaker handles inheritance. And if you go into our cue ball, you see that we now have a new create event. So it's overriding the one that we find in subpar ball. So in order to still get the effect, we can write event underscore inherited inside our create event script. And this will call any piece of code that you put inside your any parent object. So by writing event inherited, you make sure that your object still performs the event found in its parent object. So now we need to be able to pull our cue backwards, and to do so we're going to first need to be able to decide when we're pulling on the cue and when we're not. So we already have our pulling variable here, and we're going to add an event called global left pressed. We're going to add a piece of code, and we're simply going to say mouse underscore click underscore x is equal to mouse x, and mouse underscore click underscore y is equal to mouse y, and pulling is equal to true. So we can press OK, and now go inside the draw event. So this orbiting calculation here only really holds when we're not pulling on our cue. So we can write if pulling. Here we can we'll have the code that we want to execute when you are pulling on the cue, and then else we want to encapsulate all this code here that you will only be executing when you're not pulling back on the cue. So put an if pulling braces else the rest of the code, and make sure that qdir and draw sprite ext is outside of your braces. So first, inside if pulling, we want to find our directional vector again, and this is done in a very similar way, simply by doing var dir underscore vec underscore x is equal to x minus, and instead of having mouse x, we want where we originally clicked. So as soon as you click, you're locking your direction. So dir vec x equals x minus mouse underscore click underscore x. And we want to do the same with y. So dir underscore vec underscore y is equal to y minus mouse underscore click underscore y. So now we have our directional vector. Again, we need to normalize it. So first we need to find its length by doing var length is equal to vector underscore length with our directional vector x and directional vector y. Now we need to normalize it by doing dir underscore vec underscore x divided is equal to length, and dir underscore vec underscore y divided is equal to length again. So now we have normalized our vector, meaning it has a length of 1. So our next step is to calculate how far away we pulled from our original click point. So we're going to get something called a pull vector. I'm not sure if that is the technical name, but this is what I came up with. So var pull underscore vec x is equal to mouse underscore click underscore x minus mouse underscore x. And similarly for pull vec y is equal to mouse click y minus mouse y. So now we have a vector which represents the distance and the direction in which you pulled back from the original point you clicked at. However, if I quickly bring up something I can draw onto, you will see that there is a slight problem, and it's that if we have over here our ball, badly drawn ball, let me arrange it. This is pretty bad. And you clicked over here, then we have a directional vector which goes somewhat like so, if you clicked here. And then you may pull back with your mouse ending up here. And although this distance may be of a certain, like x for example, the distance you really traveled along that vector here isn't actually the same, even though we really want to know this distance here, not this distance here. So to do this, we're going to project our vector, this vector here, represented by this line, onto our directional vector. And this can be done quite simply using a dot product. So we're going to write, let's see, first we're going to write what we're doing, which is projecting the pull vector onto the direction. So first we need to get the dot product. So we do var dot is equal to dot underscore product, which is built into Gamemaker Studio, if I spelled it correctly. And this takes in a couple of arguments. So the first vector is pull vec x, pull vec y, and then our directional vector, dir vec x, dir vec y. Now we want to get our projected vector. So we're going to write var project vec x, and we're simply going to multiply directional vector by our dot product. So dir underscore vec x multiplied by dot, and var project vec y is equal to dir vec y multiplied by dot. So what we're doing here is first getting the dot product of our two vectors, which essentially represents how much of one vector, like how aligned the two vectors are. And then by multiplying our original normalized directional vector by the dot product, we can essentially pull that directional vector out by how much the first vector mapped onto the second. Essentially, we're projecting one vector onto the other. All we have to do now is calculate our q position. So q underscore x is equal to x minus q vector x. And then we want to take away a small offset. So dir vec x times 16. So we have the x position. We take away our q vector, which, by the way, right now is the same as our projected vector. So var q vector y is equal to project vec y. So our q vector right now is the same as our projected vector. And so the q x position is equal to the x position of the ball minus the q vector and we take a small offset in the correct direction. And we do the same with the y. So qy is equal to y minus q vector y minus dir vec y times 16. And make sure this is an underscore. So now all we need to do is make sure that if you release your mouse button, you're no longer pulling on the cue. So we do if not mouse check button mb underscore left, then pulling is equal to false. We can then save it, press play, and see if our code acts as we expect it to. So as you can see, we still have our cue orbiting around our object, but as soon as I click, I can now pull the cue back. However, as you can see, there is no limit, but I can pull my cue back and forth like so. And as soon as I clicked, it is locked in a single direction. So now what we want to do is make sure there is a limit to how far you can pull your cue away from your ball. And to do this, we're first going to be creating a script called clamp vector x, which I already have here, by simply creating a script over here and calling it, as I said, clamp underscore vector x. So this script will take vector x as the x component of our vector, vector y as the y component of our vector, and a maximum length. So var vec x is equal to argument 0, var vec y is equal to argument 1, and finally var max length is equal to argument 2. So first we want to get the current length of our vector, and we already have a script to do this, so we can just write var length is equal to vector length vec underscore x vec underscore y. Now we have to normalize that vector, but because we're only dealing with the x component of our vector right now, we're just gonna do it for the we're only gonna be doing it for the x component. Before we divide it, we want to make sure that our length is not equal to 0. So if length is not equal to 0, and that is because you cannot divide by 0. So when I write vec x divided is equal to length, like so, this will only happen if the length is greater than 0. If it was 0, you would get a division by 0 error. So by checking that length is not 0, you avoid getting errors. Next, we need to get the new maximum length, or the new clamped length. So get new length, and we have var new length is equal to the minimum, so the smallest between max length and length. Now we can return our scaled value. Simply by writing return vec x times new length. So here we are essentially first getting the length of our vector. We are making sure our vector has a length of 1. Then we find the new length that our vector should have, which is either going to be our length or the maximum length. And then we scale our vector by that new length again. And if I could spell length correctly consistently, it will probably help. Okay, that's good. So you can press OK. However, this was only for the x component. We also want it for the y component. So we're going to duplicate this script and rename it clamp vector y. Make sure that you change it in the title as well. And we want to change here vec x to vec y. And down here, the same, vec x to vec y. And this is it. So now back to our cue ball drawer event. We want to clamp our projected vector. So here we're going to write clamp vector. And instead of cue vector x being equal to project vect x, it's going to be equal to clamp vector x. So it's going to take as an argument project vect x, project vec y, and the maximum pole length, which we're going to set to 64. We're going to do the same for y, so clamp vector y, project vec y, project vec y, 64. And if I was paying attention to what I was doing here, I would write x and I would spell things correctly. Here you go. So var q vector x is equal to clamp vector x, project vect x, project vec y 64, and var q vector y is equal to clamp vector y, project vect x, project vec y 64. Now if we press play, we should be able to see our cue not going back as far as we used to be able to. So I cannot go any further than this. I can still go backwards, but I cannot go any further than this, 64 pixels. So now I can let go like so, and it seems to be hitting the ball, but it's not actually well, putting any movement onto the ball. So this is what we're going to be changing next. And to do so, it's really quite simple. Right here where we have if mouse check button and be left, we want to add a single line of code called physics apply impulse, apply impulse, and we're going to set the x and y pulse to x and y, and the strength is simply going to be q vector x and q vector y. Now, if we press play, we should be able to see our ball get pushed as soon as we let go. So I let go and you can see that my ball starts moving, and I can do so repeatedly, hitting the different cue balls, the different balls. However, as you can see, my cue was still attached to the ball when it was still moving. And so all we're going to add is a small line of code just before our variable declarations. We're going to write if fit underscore speed, if the physics speed is not equal to 0, then exit. What this is saying is that if we are still moving, then the rest of the code should not be executed. This is what exit does. It just exits the current event. It stops executing code. So long as you're moving, you cannot be hitting the ball with a cue ball. We're actually going to add a very similar piece of code in our global left pressed. We're going to write if fit underscore speed is equal to 0, then I am allowed to start pulling on the cue. Like so. Press save. And we can now press play and see how our cue will disappear as soon as our ball starts moving. However, as soon as your ball stops moving, you will get your cue back right about now. And I can hit more balls. So this is pretty much it for the balls. We can now start designing the table, which we can do by first creating a new object for our sides. But before, I want to spend a couple seconds, just making sure, yes, we are ready for the side. So we create a new object called obj underscore side. We're going to give it the sprite SPR side and make sure to use physics. Now under collision shape, instead of circle or box, we want to apply a custom shape. So we're going to click shape and then click modify collision shape. So we can now scale this up to something which is a bit more visible on camera. And we can start dragging around different parts of the shape to make sure that we are matching the same shape as we see on the sprite. Now I know this is flashing horribly, this is Gamemaker IDE being a bit derpy, but you just want to make sure that your shape is nicely surrounded by this box and press OK. And then under density here, you want to make sure you have it set to 0. A density of 0 will mean that it is an immovable object. It is like a brick wall. You cannot move it. It's part of the scenery. You do not want it to move. You just want it to be there so that objects can bounce off it, etc. So we're just going to press OK and then go inside our main room. And we can start placing our side objects. So we're going to start by placing 2 objects for the top of our setup. And what you want to do is make sure there is a 16 pixel gap between each of our objects. Or was it a 32 pixel gap? I need to check. No, yes, a 16 pixel gap like this one here. So I have a single grid spacing between them and my snap is set to 16. So you want to place 2 like so. Now place another one here, and here under the object tab you can add some rotation. So I'm going to add a 90-degree rotation. And this will be our left side, which you want to place so that there is just this one grid space between it. Then you want to place 2 more, and you can press the flip right button here just to flip your object around so that you can have the 2 bottom parts of your pool table. And finally place some objects on the right with a rotation of 270 degrees. You can have your right wall like so. Now if you want, you can start repositioning your balls, your pool balls so that they're centered more accurately. So they're placed as they would normally be on a pool table, sorry. So you can just shift them like so. And if you actually want to go the extra distance, you can start coloring your balls. So you can take this ball, for example, and here you have a little color option. So the first ball I think tends to be yellow, then blue, purple, or pink if you're on TV apparently. And you can go on adding more and more colors as they would normally be. I don't actually know all the colors. Actually, I think the middle one is supposed to be black, if I remember correctly. And you can go on adding all of these different colors, which you can do. I'm going to stop here, so you get the idea. You can actually recolor objects inside the IDE. You can press OK, and we can now press play. Actually no, I forgot one small detail, and that is our side object needs to have as a parent the physics object to make sure that it will interact with our cue balls and our other pool balls. So now we can press play, and it's already looking a lot more like a pool game. If I hit the balls, as you can see, they'll bounce off the different walls. And all that's really missing is a bit of decoration and, more importantly, holes for the balls to fall in. If I get this ball to get through one of these holes, you'll just see it shooting off in the distance, which isn't very useful. In a proper game, it'll just disappear, really. You're not supposed to really pay attention to it anymore. So what I'm going to do is close this and create a new object called obj_hole. Now this is going to have the SPR hole, and it is going to be a physics object. However, you do not want to have the physics object as its parent. Instead, you're going to press OK and under power ball, you want to add an event, collision with the hole, and I'm simply going to drag and drop the destroy instance icon under the main tab. and press OK. Now you just have to place your holes inside inside your room. So you have to do is place this one here, place a couple ones here, and place one right here at this gap here at a rotation of 45 degrees and a scale of 1.42. Not 1042, but 1.42. And you want to do the same over here, rotation of 45, scale of 1.42, 1.42, whoops. And add the other ones just to make it look good. One here, no need for scaling and rotation. Make sure it is again 45 degrees, 1.42, 1.42. I think you get the idea, but there is one more to do. So let's quickly do it on camera. 45 degrees, 1.42, 1.42. And you now have your four corners set up. Just to make it look a bit better, you can add a background. Maybe make it a brown for, I don't know, the floor, and then under tiles you can select your yes, you need to make sure your background is a tile set. Make it of the same size as your background, and then here you go, you can select it, place it right under your pool table, and you have got yourself something which is pretty close to a finished game. You just need to add different rules in, make sure that the balls get counted, which shouldn't be very complicated to do. As you can see, I can hit the balls. You can add different, you can make them have different sprites by adding the different image indices. And I'll just try to get a ball to land in a hole to show you that they will disappear. You can of course change the sizes of the different objects to maybe make the game easier or harder. Because as of right now, as you can see, I'm having a bit of a trouble getting the balls to land inside our holes. But yes, whilst I try to showcase that the holes do work, I'll just sign off. So thanks for watching, guys. This is it for our pool game. As you can see, it is quite simple. Box 2D makes it very, very easy to add physics into your games, even for something like a pool game. And you can use a similar stuff to make any kind of game. You could probably make a bowling game and a whole lot of other things. So yes, if you liked this, if you enjoyed this video or found it useful, please give it a like and subscribe to see more. And I'll see you guys next time. And as you can see, a ball did disappear.